I am Prajwal, and today we are going to look at this problem, planting trees. This problem is rated as easy on CodeChef, and you can solve this using some observation with prerequisite knowledge of greedy algorithms. So guys, if you haven't read the problem yet, go back and read it, try it out, and then come back and see the solution. With this, let's begin. In this problem, we are given a set of entries. Basically, we are given entries on a straight number line. These trees are actually present on the integer coordinates. We are given the position array A, where A of I represents the position of the ith tree. Now we are also given that let us consider a set of trees, and we have some trees at some location. So now we are given that these set of trees will be considered beautiful if for every tree at position x there is a tree at its neighbor. That is, for a tree at position x there is a tree at x plus 1 or at x minus 1. Now when we look at this tree, then this is not beautiful because these trees do not have a neighbor at x minus 1 and at x plus 1 considering their position as x. So if we add a tree here and if we add a tree here, then this set actually becomes beautiful. Why? Because now you can see that for every tree there is a neighbor at either x plus 1 or x minus 1. It can have neighbor on both the sides, that is also okay, but it should have at least one. In this problem, we are given the initial configuration of the tree and we are asked to find the minimum number of trees that we need to add such that this set of tree becomes beautiful. In the constraints, we are given some test cases from 1 to 1000. The number of trees can be from 1 to 10 to the power 5, and the range of this number line can be from 1 to 10 to the power 9. Now it is given that all AIs are pairwise distinct. This means that there are no two trees on the same integer coordinate. Now let us look at the test case. In the first test case, we are given 3 trees at location 2, at location 7 and at location 4. Now we need to add the minimum number of trees such that the set becomes beautiful. To do this, we can add a tree at location 3 and we can add a tree at location 6. Now we can see that all the trees have a neighbor at either x minus 1 or at x plus 1, considering its location at x. So this is now satisfied. This is now beautiful. So the number of trees that we added was 2. Hence the answer is equal to 2. Now let us look at some observations and how to approach this problem. So we are given position of entries a1 till a of n. So first of all, let's sort this as sequence because we want it be represented into a number line. So the first should be the minimum. So we get sorted A as a1 less than equals a2 up till a of n. Now we have to plant some trees such that these become beautiful. To do this, let us first plot these trees onto a number line. And we are given some trees a1, a2 and so on. Now the first observation that you are going to notice is that whatever tree we are going to add, we are always going to add it about the neighbor of some original tree. Why? Because let us say that we add it into an isolated area where it does not has any new neighbor. Then in this case, this set will not become beautiful until and unless we add one more tree beside this at position, if it is at position x, then at position x plus 1 or at position x minus 1, because this tree will become lonely and it has no neighbors. It will actually contribute more to our answer if we add it into our isolated area. So it is not optimal to add it where there are no neighbors. So we will add a new tree always at a1 plus 1 or a1 minus 1, or at a2 plus 1 or at a2 minus 1, and similarly so on. Now, in the second observation, let us say that we have some trees at some location, and let us say that there's a difference between A1 and A2. So to satisfy this condition on A1, we can add tree at A1 plus 1 or at A1 minus 1. So let us say we added this tree at A1 minus 1. Now, this tree will only affect A1 and will not affect A2, A3 or any other tree. So our answer can be basically 1 plus whatever we have left, that is from A2 till AN. And this new array is of size n minus 1. So from this you can get a intuition of greedy algorithms. Why? Because we are just satisfying it for A1, and since satisfying the condition for A1 does not affect any other tree, so our answer is basically 1 plus and whatever the answer we have for the other trees. So this guarantees that greedy solution will work. Now for the third observation. So let us consider a tree A of I. To satisfy the condition for this tree, we can add a tree towards the left or towards the right. Now it is always optimal to add a tree towards the right, because if we add a tree towards the left, then this tree will only be the neighbor of A of I, because we have already solved for A of I minus 1 and we are solving for A of I till A of n. Now adding a tree towards the right would give this newly added tree a chance to be a neighbor of both A of I and A of I plus 1. Now if the distance is more, then we either have to add this tree towards the left or right, and adding it towards the right makes more sense. If the distance is more, then it does not matter, we add it towards the left or right. We will just simply add 1 and we'll solve for ai plus 1 till a of n. So now these are the main three observations that we needed for this question, and we will use this to formulate our solution. Moving on to the solution. Our solution basically rests on these two observations. So what we can do is we can iterate over all the trees. So we iterate from I is equal to 0 to n, and we check for the current tree that whether a of I minus 1 belongs to a or a of I plus 1 belongs to a. This basically means that for the current tree at location a of I, whether there exists a tree at location ai minus 1 or at ai plus 1. If this is the case, then we just continue, because this tree already has a neighbor. Else we increment our answer by 1, because we now have to add a tree, and from observation 2 we can say that we will add a tree towards the right. So we will append a to a of I plus 1. Now to perform this searching as well as adding new elements efficiently, we can use a data structure set or a heap to do this. So this will offer us a complexity of order of log of n for searching as well as adding new elements. Remember that we need to maintain the sorted order of A. Hence adding new elements will be order of n in A. Now the time complexity will be order of n log n. Why? Because initially we have to sort this array A, as well as we are doing n searching or adding operations using a set or a heap, which is n log n. The space complexity is going to be order of n, because we need to store the order of n integers that are the locations of the trees, and in the heap we will store order of n trees, because for every tree we can add a new neighbor. So in the worst case we will have 2n trees. Now let us look at the code. Firstly, I have processed the input. I have taken the variable ARR to store the positions array. Now there is this base case that if n is 1, then we can simply output 1, because if there is one tree, then we need to add one more tree to satisfy the beauty property. Now we will sort ARR according to their position in increasing order. and I have created this variable set that will tell us the current number of trees that we have. This will include all the original trees as well as the trees that we add. The size of this trees set can be at most 2n. Now we iterate over all the trees, and if there is a tree at right or a tree at left, then we just continue, else we will add a tree towards the right. Finally, our answer is the difference between the final trees that we have and the original trees that we had. So we output our variable answer. So guys, this is pretty much the whole code. Try to code it yourself, and if you face any issue, then come back and see it again. So guys, I hope you understood the problem clearly. If you have any questions, drop a comment in the comment section, like the video, and don't forget to subscribe to get our latest updates from CodeChef. Thank you and goodbye.